We have ended the previous lesson with the realization that the private key of a CA is extremely valuable, as each certificate is validated based on this private key, and this realization led us to the question of whether there is a way to reduce the frequency of usage of this private key, as each time the private key of the CA is used to sign a certificate, the private key is exposed to the risk of being misused or the risk of being leaked. This is an important challenge to solve, and this is also the key motivation for the actual architectural specification of X.509 PKIs as defined by RFC 5280. In X.509 PKIs, there isn't just simply one CA responsible for the issuance of certificates, but X.509 PKIs have the flexibility to create hierarchies of CAs. On the top of this hierarchy, X.509 PKIs have a root CA, which is simply a CA as well, and as such has a public-private key pair for digital signature purposes, but with the root CA not being subordinate to any other CA, which in this context then really means that the public-private key of the root CA is not certified by any other CA. One level lower in this hierarchy are issuing CAs, which again are simply CAs and as such have public-private digital signature key pairs as well, but this time these issuing CAs are subordinate to a root CA, which really means that the issuing CAs have their public-private key pair certified by the root CA. In the drawing on the left, this relationship of having a certified key pair is indicated with purple dashed arrows, which for example now points from the issuing CAs to the root CA, as the root CA certifies the key pair of the issuing CA. If we look at the top of the drawing, we see a circular arrow, and this really is accurate, as in an X.509 PKI, the root CAs have a public-private key pair not certified by any other CA, but with their key pair being certified by themselves, which is then referred to as the root CAs having a self-signed certificate for their public-private key pairs. Importantly, the idea is now to keep these root CAs such that they are only used to create certificates for other CAs, but that they are not used for the creation of any other certificates, like for example the end entities Alice and Bob. Issuing certificates to end entities like Alice and Bob is then the responsibility of the issuing CAs, and if these ideas are properly followed by a PKI, the effect that this has is that there will be very little activity on the private signing key of the root CA, as very often the number of issuing CAs in a PKI is usually very small, with a number somewhere between 1 to 5, and the second effect occurring if these ideas are properly followed is that the issuing CAs will then be the CAs that will see a high activity of their private signing keys, as the issuing CAs will be the ones that issue certificates to end entities, which can, depending on the purpose of these PKIs, easily reach into the millions. Great! This architecture seems to have an interesting effect on the activities of the private keys of the CAs. Let's see how a trust model can now be defined for X.509 PKIs such that the overall risk of having misused or leaked keys is significantly lowered. The trust model in X.509 PKIs is now as follows. Trust within X.509 PKIs still means to trust the accuracy of the certificates issued, especially in the binding of the public key to the end entity listed as subject in the certificate. Now, very interestingly, trust within X.509 PKIs is transitive, meaning that if a CA is trusted, all other CAs are trusted as well that are certified by this initially trusted CA. If end entities now trust the root CA, then by virtue of the transitive trust model, the trust will manage to range across the whole PKI, starting from the root CA, with the trust then extended to the issuing CAs certified by the root CA, and finally with the trust then being extended all the way down to the certificates issued by the issuing CAs. How cool is that? The effect all of this now has is that all of the trust in an X.509 PKI is now anchored on the private signing key of the root CA, which has very little activity as it's only used to sign a small handful of issuing CAs. And the second effect this trust model now has is that in order for an end entity to validate a certificate, it's now not only required to validate just a certificate, but it's required for the end entities to now also validate a chain of certificate that needs to lead from the end entity certificate all the way up to the certificate of a trusted root CA. The requirement that end entities now have to validate chains of certificates and not just single certificates before they can use the public keys contained in the certificate is the immediate consequence of the powerful transitive trust concept presented on the previous slide. To validate a certificate, the end entities need to be provided with a chain of certificates where the start of the chain is the end entity certificate to be validated, where at the end of the chain of certificates needs to be a certificate of a trusted CA, which will very often be a trusted root CA, and where the certificates in between the start and the end are just the certificates of all the CAs making up the path from the end entity certificate up to the root CA in the PKI. Starting with the first certificate in the chain, which is just the certificate of the end entity that one wants to securely communicate with. This certificate itself is just simply validated by validating each field according to the semantics of the field as we have learned in a previous lesson. Once the validation of the certificate reaches the validation of the digital signature contained in the certificate, the public key of the CA listed as issuer on the certificate is required, and this public key can then simply be retrieved from the certificate one step further up in the provided chain of certificates. If also the validation of the digital signature succeeds with respect to the public key retrieved from the certificate one place further up in the chain of certificates, then the validation of the current certificate is considered to be successful, and the validation of the certificate one slot higher up in the chain of certificates is next. If this validation succeeds for each certificate in the chain, and the last certificate in the chain is the certificate of a trusted root CA, the overall validation succeeds, and the end entity can then consider the public key contained in the certificate at hand as authentic and can proceed to use this public key for the intended cryptographic purpose, such as to, for example, encrypting the data sent to a communicating peer. This is it. This is how X.509 PKIs work on an abstract level. Try to make sure that you intuitively understand everything presented in the course so far before proceeding to the next chapters, where we will apply the theory by constructing from scratch such a two-tier X.509 PKI as presented on the left, and where we will make use of the constructed PKI to secure the exchange of emails.